All right, ladies and gentlemen, we're going to go through a quick video on how to handle vectors in physics. And we will use this throughout all portions of physics. This is basically geometry and trigonometry. So it's a quick review on that and how to apply it in physics. So we're going to start with vectors now because we're going to be dealing with motion in 2 dimensions. Since a projectile moves both in the up and down direction, the y direction, and the side to side direction, the x direction, then that means that the vectors that represent projectile motion will have 2 components to those vectors. They will have both a x and a y component. So far we've just been talking about things that go straight up and straight down or straight side to side. But now we need to be dealing with things that we can describe at angles. All right, so the difference between a vector and a scalar is a quantity that has a magnitude or an amount but doesn't have a direction. So speed, volume, and mass, those are all scalars. Vectors, however, require a direction to be fully specified. So velocity, you have to know the direction for velocity to be fully specified. Displacement, force, there's all sorts of things that are vectors in physics. Okay, when we notate vectors, typically you see it with a bold R or an R with an arrow vector over it. But be flexible about that. Sometimes you just have to realize that you're talking about a vector. But typically, you can expect to see this kind of notation when you're dealing with a vector. You draw a vector by drawing that vector from the tail to the tip. So this is the tail of the vector, and that's the tip of the vector. And so this vector has a magnitude that's this long, and its direction could be described as this angle from the horizontal or this angle from the vertical. It depends on the frame of reference. So a couple of ways to add vectors. We can use the tip to tail method, which is pretty straightforward. It just means that you add the vectors up by just putting them together tip to tail. And quite often we'll have that situation when we have when we're able to set up that situation, and we can have a right triangle like this, and that simplifies things an awful lot. So oftentimes we will have an x direction, a y direction, and then our vector will be the hypotenuse of that distance. So this is not at all uncommon that we're doing this tip to tail method. You don't always set this up. Sometimes it happens organically, and I think you'll see that in just a moment. And the resultant vector is that vector that goes from the beginning of the first vector to the end of the last vector. So this resultant vector would point along this line. Another way to do it is to take the 2 components of the vectors and put them together into a parallelogram. In this case, we're going to have a rectangle. We're just going to reproduce the y vector, reproduce the x vector, and then put a resultant as a diagonal of that parallelogram. Sometimes that's easier, sometimes it's harder. So either use the triangle or the parallelogram method. Which one's easier? Okay, one really, really key thing about working with vectors is they have to have the same units. So you have to be dealing with the same quantity. So for example, here we might have a velocity vector in 4 meters per second, and we can add to that another velocity vector at 3 meters per second. So they're both velocity vectors, and they're both measured in the same unit. So then whenever we find the resultant of 5 meters per second, then that makes sense. You couldn't have a velocity vector here of 4 meters per second and an acceleration vector here of 7 meters per second squared and expect to get anything that made any sense over here. These always have to be the same. So same variable, in this case all velocity, same unit, in this case all meters per second. Okay, so resultant vectors, let's see if we can practice that a little bit. It shouldn't come as a big surprise to you that this equation, C equals A plus B, is kind of a geometric interpretation of resultant vectors. And if they point in the same direction, if A and B do this, then that's super easy. A plus B, in this case, is just going to be 25. So A plus B equals C. That's pretty straightforward. If they point in the opposite direction, so these are collinear vectors, then this would be a situation of A minus 10. So this would actually carry a negative sign on it. I kind of don't like the fact that it doesn't because the resultant vector here would be 5 meters. And if you think of this from a tip to tail method, then this is tip to tail, and we can see how long it gets. If we were to do the second one tip to tail, then we would have lifted this one up here and brought it back this direction, and we would have been able to see that the resultant vector was just 5 meters. Okay. Another way you can calculate the magnitude of a vector when you have them and they're not collinear, like we just saw, is we have to use the good old Pythagorean theorem. So c squared equals a squared plus b squared. You'll get so you can use this in your head really fast because we need to use it a lot. So in this case, as you recall, if I have a vector of magnitude A, a vector of magnitude B, then the length of the magnitude of the hypotenuse of that right triangle would be C, according to good old Pythagoras. So let's try this idea right here. If Emily kicks her soccer ball 6 meters to the right across the field, so 6 meters straight to the right, and then Kara kicks it 14 meters straight ahead, then what's the total displacement? It's going to be a triangle. We just put it into the a squared equals b squared, c squared equals a squared plus b squared, and solve for c to get the distance, and that's all this is. This is the square root of a squared plus b squared, and that gives us distance. So that's the magnitude. So this is kind of showing us in a picture. So in a picture, this shows us what's happening. So this is the distance we're after. Here's our distance A. Here's our distance B. Notice that this is a negative sign. Apparently down or going down on the screen is negative according to this frame of reference. However, it doesn't matter whenever you square it. And then if we take the square root of the sum of these two values, then we should get the distance that the ball is from its starting point is 15.7 meters. Okay. Now we have Carol and Robin. They're sharing a house, and to get to work, Carol walks 2 kilometers north while Robin drives 7.5 kilometers east. How far apart are their workplaces? So they both start in the same place. And so this is apparently where their house is. And Carol goes this way, Robin goes this way, and they end up that far apart. So this should look a little bit like the parallelogram method, that if we were to reproduce this side over here and reproduce that side over there, then we'd be able to see that this is the diagonal of a parallelogram that is made from those two sides. So this is the same a squared equals b squared plus c squared. This is c. That's what represents the c in Pythagorean's theorem. They're calling a this side and b this side. So if we solve this before we put numbers into it, we just take the square root of both sides. So it just becomes d on this side, and then it becomes the square root of the sum of the squares of those two. We drop the values in, and notice in this case there's no positive or negative indicated in these values, so that would say to me that this was the positive direction for this value and this was the positive direction for that value. And we come up with a distance between their workplaces of 7.76 kilometers. So this is a little bit misleading because it actually means that this distance right along here is 7.76. But you can get it either way because the diagonal is going to be the same length either way. It's just a difference in the way it's drawn. Okay, so now we've got a similar one. If you drive north for 405 meters and then west for 470 meters, how far are you from your starting place? And what distance did you travel? Okay, Well, the distance you traveled, the second part of this, that's just super easy. Distance is the sum of the path traveled. Well, there's part of the path, there's the other part of the path. Add those up, that's the distance traveled. How far you are, that's this displacement piece right here. Okay, so be careful with this notation because this is showing change in x direction and this is showing change in y. This does not mean displacement. That's a little bit, I'm not sure I like that notation. So if we look at this, then we're going to have to use Pythagorean theorem to figure out this distance because we know the length of each of the sides of a right triangle. So hopefully if you took time to figure that out, you got a displacement of 486.7 meters when you took the sum of the squares of those and took the square root of it. You should have gotten that. And 675 is simply the sum of those two. So that one wasn't too bad. Okay, here's another one. Now we've got an airplane that flies due west at 150 kilometers per hour into a headwind. Okay, that means a wind that's blowing toward the airplane. And it's 25 kilometers per hour. What's the resultant velocity of the plane? So this one's really easy. This is not one where we have to use any kind of a triangle. This is one where we have two vectors that are collinear. So if we look at this as being a tip to tail, these are drawn so that they're just collinear. But if we did it tip to tail and we did 150 meters this way and then 25 meters back that way, then our resultant vector would just be that what was left. So it doesn't take rocket science to figure out that the resultant should be negative 125 kilometers per hour toward the west. Okay, so now we have a ball rolling on a porch. It rolls 60 centimeters to the edge of the porch. It drops 40 centimeters. Then it rolls along the grass. We're assuming it rolls along a flat piece of grass and stops 80 centimeters from the porch's edge. What is the magnitude of the ball's net displacement? So we actually have two displacements in the x direction. The 60 and the 80 are side to side or x direction displacements, and the 40 centimeters is a y displacement. So, uh-oh, darn it. So if we were to draw this, I would draw this as being 60 centimeters plus 80 centimeters along this way, and then a 40 centimeter drop, and then find the ball's displacement based on that. So work on this one and then compare it with one another and see if you agree with one another. All right, so that's the end of this part one of the vector videocast. We'll continue in just a minute with the other half of it.